Kia ora koutou. Welcome back to Math 101. We're nearing the end of the course, so we've got 3 more weeks to go of teaching. But really, this week, we cover the bulk of what we're going to do with integration. We've got a little bit more integration content next week, and then we move on to applications and revision. So hang in there, we're nearly there with covering new content. And then we've got week 12 of revision, and we've got study week, so we've got that time, we've got some weeks ahead of us to catch up if we need to consolidate our skills and make sure we get lots of practice for the exam. So a couple of things before we get started today. Kia ora, my name's Rosie, so I've been bugging you with emails from Learn all semester. So I'll be taking the next 3 weeks of the course up until the end of semester. If you want to drop by and say hello, if you've got questions or you want to chat about how the course is going, you're welcome to drop by my office. I'm in Jack Erskine 410. I've got drop-in hours, so office hours, 1 to 2 p.m. Monday and Tuesday. But if you're around other times and my door's open, you're welcome to drop in at those times as well. So come and say hi, ask questions, raise concerns, and we'll see what we can do to help you out. So a couple of other notices. So Lab 9 question set is due on Tuesday, as always. If you haven't started, I do suggest you start that ASAP, because the next couple of lab question sets are a little bit more challenging than previous ones, as we get stuck into calculus and applications of calculus. So make sure you leave yourself plenty of time to work through those. If you haven't done them yet, the CAP quizzes are a good thing to do to work through those, because that's an extra 5% towards your final grade, which doesn't sound like much, but it's a whole grade step. So that's like from a B minus to a B, or an A minus to an A or something. Yes?
Are those the CAP quizzes from the beginning of the year, or are they new ones?
No, they're the CAP quizzes that have been there all semester. So a lot of people have already worked through them, but some people haven't. So if you haven't done those yet, then you should get onto that. And then finally, if you've been uploading lab working online instead of the attendance grade, make sure you're going back to check that feedback. So you can click on the lab working link where you originally uploaded, and you can see a little bit of feedback there. So you may have lost marks if you didn't submit the right questions or didn't have full working, but I think most people got all the marks once they'd done the upload. So that's it in terms of kind of housekeeping notices. So let's get stuck into some calculus. So I'm going to start with a brief review question, just to help you out if you're working through Lab 9. So we want to differentiate. So we remember, okay, what are our rules for differentiation? We can check our formula sheet for our sort of standard ones. We've also got the product rule, the quotient rule, and the chain rule. And looking at this, I can see I've got my log function on the outside, and then I've got an inner function of this quadratic. So I've got an outer and inner function, which means I need the chain rule. So if I want the chain rule, my first step is identify my inner function and my outer function. So my inner function I'm going to call u of x, and that's my quadratic, 4x squared minus 3. And then my outer function, y of u, says if I replace all of this with u, then I'm left with the function ln of u. And then my chain rule is dy dx is dy du times du dx. So I can differentiate each of these separately and multiply those together. So dy du, so if I differentiate ln of u with respect to u, that becomes 1 on u. if I differentiate u of x with respect to x, that becomes 8x. And then I want it in terms of x, so I'm going to take that u and substitute in back my quadratic. So I end up with 8x on 4x squared take 3. So that's my derivative of this chain rule function. So my steps there were I identified which rule I wanted to use, and then I identified the different components that I needed. So I needed an inner function and an outer function. So I can label them if that helps. And then I put the pieces together to apply that rule. So that's a brief recap from the chain rule, which we covered last week. But if you do have questions about, well, this example or any of the questions in Lab 9, then do come and ask me, or you can go to the lab sessions or the online help sessions to ask tutors for help. They'd be very happy to see you because they love working with you guys. And often there's not that many people in the lab, so there's always space for more people if you want to go to multiple computer lab sessions. Okay. So we've looked at how to differentiate functions, and we want to keep an eye on why are we doing this. So we've thought about some different uses so far for differentiation. So we've seen that it gives us the instantaneous rate of change. So calculus really is about studying change, rates of change. We've looked at how if I have a function, maybe something like this, and I want to know what's the slope of this function at a particular point, then I can use the tangent line to that point. And that tells me how steep that curve is at that point, what the slope is. So differentiation is the process that I use to get the slope of that tangent line. And then once I've got the slope of a line, I can find the equation of a tangent line. And then the other thing we've done is we've used differentiation to help us sketch graphs of functions. So if I've got a cubic function, last term we figured out how to find the intercepts. So I could go, well, maybe my function looks like this because I know where it crosses all the axes. But then using differentiation, we're also able to find the turning points when that derivative equals 0. So we can add some more detail to our sketches. So today week, great. Tomorrow we're moving on to something else. Today we're looking at some optimization. So finding absolute maxima and minima over specified intervals. So if I've got some function and I've got some function f of x over an interval, maybe I've sketched it from 0 to 10. I want to know maybe what's the largest value that function reaches over that interval, or what's the smallest value. And then later on this week, tomorrow, we're going to look at reversing differentiation, so we'll look at integration. So for today, we're looking at absolute extrema. So this means the extremes of a function, so the maximum and the minimum of a function. And this might be useful because we might have some sort of, imagine we've got like a cost function for building something, and we want to find the cheapest way to build it. We want the minimum of that cost function. So anytime we have some sort of model, it might be really useful to know when is the maximum in that model and when is the minimum. So that's keeping in mind why we're doing this, because often what we want to do with functions, with models, is optimize them, find the maximum and the minimum. So this slide here I know is a wall of text, but that's for you, it's basically there for you to come back to later to remind you about the extreme value theorem. But basically this says if I've got a function that I'm interested in, so I'm interested in my function f of x. We know a couple of other things about f of x. We know that it's continuous over a closed interval. We'll see shortly why those two conditions are important. But for now, suppose we've got our function. This just says that the smallest value over that interval is what we call the absolute minimum. So we refer to absolute minimum and absolute maximum because if I have a function like this over my interval, I've got my absolute maximum here. But I might also be interested in this turning point, so I might call that turning point the relative maximum. Or a local maximum. So that means if I was to zoom in on this part of the function, that turning point will be a maximum on that smaller interval. But if I'm interested in this whole interval here, then I might want to know the absolute maximum, which in this example turns out to be that top point. So that's why we say absolute, is to distinguish between relative maximum and minimum. Okay. So a brief example. We won't get into the algebra in this example, but we'll look at the graph just to make sure we know what we're talking about. So I've got a function in all of these examples with the extreme value theorem. I've got a function that's continuous on a finite closed interval. So that means I'm looking at, it starts at some number. So in this example, -3/2, and it goes up to some other number, 3. And it's closed. So we've got those square brackets. Remember, those square brackets mean closed interval. Okay, so if we just look at this graph, where is our absolute max and absolute minimum? What do we think? Yep, so the absolute maximum to start with? Yep. Yes, so the highest point, right? We can just see it on the graph in this example. And so that is the point 312. And the absolute minimum yeah, so whatever that turning point is, and we'd need to differentiate to find exactly where the turning point is, but let's just call it approximately. Let's call it 1.5 and 1 and a bit. Let's just call it 1. So that point there, so the turning point. So we can see on this graph where that point is, but we can also see, like if we zoom in, it's actually not exactly at 1.5, 1. It looks a bit more like it's maybe 1.6 for the x value. But remember, we know how to find turning points. We can use differentiation. So we could use the derivative to find the turning point. I won't do that on this example because I've got some more examples coming up. Okay. So I've said a few times that we've got this interval we've got this function that's continuous and it's on a closed interval. So let's pause briefly to think about why are we saying that? Why do we care about those conditions? So first of all, what happens if our interval is not closed? So remember, closed is something like AB. So this is certainly not a closed interval. We never have x equal to 1 because I've used a round bracket, and then it decreases without bound. So I've got negative infinity as my left-hand bound, so that's always an open interval. So can we find an absolute maximum? No, why not? Yeah, there's no x point. That's like if I wanted an absolute maximum, it would have to be, x would have to be as large as it could go over this way, but I never actually have a largest x value in this interval. I could say, well, what about x equals 0.9? Well, that's not my absolute maximum, because if I have x equals 0.99, that's going to be even higher. Or 0.99999 is going to be even higher than that. So we don't have, it's not that, it's not that, it's not x equals 0.9. So there's no absolute maximum because there's no largest x value. What about absolute minimum? Do we have an absolute minimum? No. So again, like looking at the graph, the same kind of thing is happening. My y value keeps getting smaller and smaller. And I could just keep picking a smaller and smaller x value, and my corresponding y value would be smaller and smaller. So again, there's no smallest x value. Because it continues to negative infinity. And remember, negative infinity is not a number. It's a symbol that means we keep decreasing forever. Okay, so if I have an open interval, either using infinity or just using a round bracket, then I may not get an absolute maximum or minimum. So what about continuous? What if the function's not continuous? So in this example, this is not continuous because I can't have x equals 3. So I've got my interval from 1 to 5 that's closed. So that's great. But x is not equal to 3 because otherwise we'd be dividing by 0. So f of 3 is not defined. And so if I wanted to find the maximum, this is a particularly unlucky example because if we're just looking at this graph thinking, where do I think the maximum is? Well, that's going to be the point that we choose, but we're not allowed to choose that point. So we want to choose x equals 3 as the maximum, but we can't. So there's no maximum. And like in the last example, you could say, well, what about if I chose the point just to the left or just to the right? But again, we run into the same problem as trying to choose the maximum here, is that we could always choose something slightly bigger. All right. We do have minimums in this example. So the absolute minimum, there's actually 2 of them, and they happen at x equals 1, y equals 0, and x equals 5, y equals 0, because that is closed. So if it's not continuous or it's not a closed interval, maybe we'll have a local maximum or minimum. But we've seen that we don't necessarily have this maximum or minimum. And so that's why when we're looking for local, sorry, did that microphone cut out? Okay. Is that better? Yes, good. Okay. So if we're looking for extreme values, absolute max and min, then we're just going to say, okay, let's only look at the cases where we know we're going to find them, when it's closed intervals and continuous. So I won't say much about this slide except that it might be useful to refer to later. This gives us step-by-steps for how to find the absolute extrema. So it says, fairly intuitively, if we're looking for our absolute maximum or minimum, there's two places we need to check. One is a stationary point or a turning point, and the other is the endpoints. And so we could think of our little cubic function like this. Our absolute maxima or minima, oops, there you go. Our absolute max and min are going to occur either at the turning points or at the end points. So that's what we need to check. And we basically check all of them and see which one is the biggest, which one is the smallest. And so that's what our steps say. Find our stationary points using our derivative. Then, so first find the stationary points, then calculate all the values, and then compare and choose the biggest and the smallest. And that's your absolute max and minimum. So let's practice that. But of course, we also want to practice asking ourselves, does this function meet the conditions? So if I look at this function x squared on this interval, does it meet the conditions of our extreme value theorem? So is it a closed interval? Yes, we've got square brackets in our interval, so yes. And is it continuous? Well, it's just a quadratic. We're at no risk of dividing by 0 anywhere. So yes, it's continuous. We want a quick sketch. We can sketch this quadratic. That's an easy one to sketch. Something like this. Great. And we could just look at this quadratic and think about, oh, I've sketched too much. My interval was just from 2 to -2, so it should be stopping here. There, that's my function. So the absolute maximum, I can see from this example, is going to occur at my endpoints. So there's one at 2, 4, and there's one at -2, 4. And then we can see that the minimum occurs at the turning point, at that vertex, at 0, 0. So that's great if we've got a really simple function that we can just sketch and see exactly where the turning points are, exactly where the endpoints are. What about something like this? We've kind of seen similar examples. So to start with, I can see I've not got a closed interval. So no, it's not a closed interval. It is continuous on this interval. And so as I said before, we don't know that we're necessarily going to get a maximum or a minimum, but we could still see what we can find. So if I sketch this, there. I'm going to put an open circle there because we don't actually, we do keep going forever. I'm just not going to see it. So it's going to keep going like this. Okay. So there's no absolute maximum because we don't ever have x equal to 0. And so that's where our open bracket is. So we've got open interval at that end. So we're not going to have an absolute maximum, but there is an absolute minimum. So that occurs at x equals 4, y equals 1 on 4. And that's because we've got that closed interval there. Okay. So now we're going to get to something that's a little bit more complicated. This is just a quadratic, so we could just sketch this. But if we wanted to start working through things more algebraically, let's start using that algebraic method and that checklist that we looked at earlier. So first of all, I want to check if I can use the extreme value theorem. So is it continuous? Well, it's just a quadratic, so that's going to be continuous. And is it a closed interval? So the interval is from 1 to 4, and it can be equal to those, so that's square brackets. So yes, it's closed. So that's our first step. Our next step is to find the turning points. And so you could complete the square and find the vertex because it's just a quadratic. But our more versatile method is to find the derivative. So derivative of this is 2x, take 4, and set that to be 0 to find my turning point. So 0 equals 2x, take 4, 4 equals 2x, x equals 2. So we've got our turning point at x equals 2. And if we flick back a couple of slides, our next step is calculate the values at the endpoints and at the turning point, and then compare all the points of interest. So what I'm going to do is think about my points of interest, or the points to check. And I'm going to compare the output values, the y values or the f of x values. So I want to check the endpoints, x equals 1 and x equals 4. And I also want to check any turning points in that interval. So I'm going to check x equals 2. So I've got my endpoints to check, and I've got my turning point to check, or stationary point. If I put 1 into f of x, I get, so f of 1 is 1 squared, take 4 times 1 plus 5. So 1 take 4 is negative 3 plus 5 is 2. If I put 2 into this function, I get 2 squared, take 4 times 2 plus 5, and that comes out to 1. And if I put 4 into this function, f of 4 is 5. And so I look at these and go, which one's the smallest? Well, 1 is my smallest y value, so that's my absolute minimum. So my absolute minimum occurs at this point, x equals 2, y equals 1. And then I look at these values and say which one's the biggest. Well, 5 is the biggest y value. So I'm looking in the second row, I'm looking at these numbers and going, which is the biggest, which is the smallest. So my absolute maximum occurs at this point, x equals 4, y equals 5. So that's our process. We check if we can use the extreme value theorem, then we find all our turning points, and then we check our turning points and our endpoints, pick the biggest and the smallest, and then we're done. We could sketch it as well if we wanted to check. So I could sketch this. And we could start by using this information. So I'm interested in x's from 1 to 4, so that's my domain. So I have 2, when x equals 2, y equals 1. When x equals 4, y equals 5. So we can use these points as well to make a little sketch. And we can see we've got a minimum at the turning point, and our maximum is at that end point. So a sketch is a really useful thing to check your answer. And you could do that on paper. This is a quadratic, so should be used to sketching that by now. Or you could chuck it into something like Desmos to check where's my maximum and minimum, do my answers line up and make sense. Any questions about this example or this process before we look at another example? Is that a question? No. Okay. So if we don't have something like a quadratic, so cubics, we have practiced sketching these, but this one could factor out a little bit to simplify. But if I don't want to go through the whole process of sketching this cubic, I'm just interested in finding the extrema, the absolute maximum and minimum. So first step is check our conditions. Is it continuous? Well, it's just a cubic, so we know that's continuous. What's our interval? From 0 to 12. And I've got equal signs, so that's square brackets, it is closed. Great. Next step, we want to find the turning points. So that means we need the derivative. So let's find the derivative of this. So we remember, take that power and bring it down. So our rule for t cubed is that becomes 3t squared, but we're dividing by 3. Take, multiply by 2, so that becomes 12t plus 32. So it's t squared, take 12t plus 32. So we want to find when is that equal to 0. So we could use the quadratic formula, or we could factorize, and I'm going to factorize that as t minus 8, t minus 4. So our turning points occur at x equals 8 and 4. So then next we want to compare our different points. So what points do we want to check? We want to check the end points. Oops, t. So our end points are 0 and 12, and we want to check these turning points, so 4 and 8. So we've got 4 different values we want to check. So if I put 0, f of 0, if I put 0 in here instead of t, I end up with 0. F of 4, if I have 4 cubed on 3, take 6 times 4 squared plus 32 times 4. We could calculate that out. I won't run through the arithmetic, but we end up with f of 4 is 160 on 3. F of 8 is 128 on 3. And f of 12 is 96. So I'll leave that for you guys to check that working, check that you put those values in and get the same answer out. And so then we look at these values and we think, what's the smallest? I'm looking at my F values now and thinking, what's the smallest? So I've got certainly 0 is the smallest, and then 96 is the biggest. So that tells us our 2 extrema. So absolute minimum at that smallest value, so 0, 0. Absolute maximum at the largest point when f is 96, so t is 2. So in this case, it turns out both of our endpoints were our absolute extrema, but we do need to check those turning points because we don't know what our graph looks like. If we were to sketch it, then it would look something like this. We're going from 0 to 12, and we know we've got turning points at 4 and 8. And it's going to look something like this, where we get up to 96. And I know that that point here, when t equals 4, we get 160 over 3. And when t equals 8, I get 128 over 3. So while that's not to scale, I know that this number is going to be bigger. So that turning point is going to be relatively higher. We get a relative maximum at t equals 4. So that's just highlighting what's going on in this graph. We're not really going to be focusing on relative maximum and minima. But we have practiced sketching these polynomials, so finding where these turning points are and classifying whether or not they're a local maximum or minimum. And now we're thinking a little bit beyond that and saying, what if I've got an actual problem I want to optimize? I might not care about this local maximum. I might care about overall, what's the largest output value I get in my domain that I care about. So are there any questions about this example or this process so far? And as always, it can be a really useful tool to get to the end of this and then sketch your graph on something like Desmos so you can check your answer. Any sort of checks you can build in as you go can be really useful. So far we've looked at like quadratics and cubics and things that we already know how to sketch. But what if we have a function that we don't really know how to sketch by hand yet? So what if I've got some sort of function like this, 2x times e to the power of negative 3x. So I wouldn't know how to sketch that without putting that into something like Desmos. And again, we don't particularly care about whether we can sketch it. We care about finding these extrema. Can we find the absolute maximum and minimum? And we have algebraic tools to do that. That's what we've been working through already. So our first step is we want to check if we can use the extreme value theorem. So check, is it continuous? And is it a closed interval? Well, the interval has square brackets from 0 to 3. So yes, it's closed. And while I don't know what this function looks like, I can tell that if I put in any number between 0 and 3, then I'm not going to get any discontinuities. I'm not going to ever be dividing by 0. That's the main thing we want to be watching out for in this course about discontinuities. So it is continuous. Nothing weird is going to happen in that interval. So our next step is find the derivative. Because we want to find if there are any turning points, and if so, where are they? So we want to find the derivative of this function. Well, it's good that we've practiced lots of tools for finding the derivative. It's not just a polynomial anymore. Now we've got this product function. So I want to use the product rule. And I know you guys are still practicing that in Lab 9, so I'll step through some of this. So we've got f of x is 2x times e to the negative 3x. So I'm going to have that as my two functions. So u is going to be the function 2x, and v is going to be the function e to the negative 3x. So that's my two functions that I'm using for the product rule. And then if I want to find the derivative using the product rule, I'll do it here. F dash of x is going to be the derivative of u times the function v plus the derivative of v times the function u. I think in the formula sheet I use g and h. But it's the same thing. You can see I'm just swapping out different letters. So that means we want each of these smaller derivatives. So the derivative of u is just going to be 2. And derivative of v, for this one we need to use the chain rule. If I want to find the derivative of this function, I'm going to need the chain rule. And because I've got a really simple inner function, I'm going to do that in my head. I know the derivative of this inner function is just going to be negative 3. And the derivative of e to the power of something is just e to the power of that same thing. So here we use the chain rule. And if you're still practicing and still getting used to these, then you may want more steps in working out that chain rule, and that's fine. Write as many steps as you need to so that you don't lose where you're up to or make mistakes. So now I've done my different components, and I can put it together to find the derivative of my function. So that's going to be 2 times e to the negative 3x minus, so I've got a negative 3 there, so that becomes minus 3e to the negative 3x times 2x. So that is 2e to the negative 3x take 6x e to the negative 3x. Okay. So if we want to find turning points, we want to solve 0 equals this guy. 0 equals 2e to the negative 3x, take 6x e to the negative 3x. So if I was to start rearranging this, this is a harder problem. If I was to start rearranging this, I might go, okay, let's add this term to both sides. So I end up with 6x e to the negative 3x equals 2e to the negative 3x. I might get a little bit stuck here. What I'm actually going to do instead is take this expression and factorize out that common term of e to the negative 3x. So let's ignore that line for now. And I've got 0 equals e to the negative 3x is my common factor, and 2 minus 6x. And remember, if I've got the product of two things and they multiply to give 0, then at least one of those must be 0. So either So either 0 equals e to the negative 3x or 0 equals 2 minus 6x. If I want e to the power of something equals 0, that's actually not going to have a solution. So if I think about my exponential decay, that's never actually going to reach 0. So there's no solution there. But if I have 0 equals 2 minus 6x, that's just a linear function. Add 6x to both sides, divide by 6. X is going to be 2 on 6, or 1 on 3. Okay, so where are we up to? We are finding the derivative so that we can find the turning points. So we found a turning point at x equals a third. And now our next step is check our points of interest. So we want to check the y values for our endpoints. So our endpoints are 0 and 3. And our turning point happens at a third. So if let's remind ourselves our function is 2x e to the negative 3x. So if I have 0, if I put 0 into this function, I'm going to get a 0 there, so it's just going to be 0. If I put a third into this function, I get 2 times a third, so 2 on 3, times e to the power of negative 1. So I can simplify that a little bit by going, I know that's 2 on 3e. And then if I put f of 3, I get 2 times 3, so 6e to the power of negative 3 times 3, so negative 9. So it's going to be 6 on e to the 9. And then I want to think about which of these is the smallest y value. What do we think? Quick voting system. So 1 finger up if you think it's 1 finger, 2 fingers, 3 fingers. So if you were looking for the absolute minimum, so do we think it's the first point, the second point, or the third point? Vote. Good. Excellent. Everyone's putting up 1 finger. So this is our absolute minimum, because these are both positive numbers. So our absolute minimum occurs at 0, 0. What about our absolute maximum? Can we vote on that too? Which value do we think? Fewer people voting. Okay. We're a little bit divided on this one. So if I'm comparing these numbers, ultimately I could just put them both in a calculator, right, and check which one looks like the largest number. But I could also think about this. Remember that e is about 2.7, which is a little bit less than 3. So this first number, 2 on 3e, is going to be 2 on 3 times 2.7. So it's roughly 2 on 9. 3 times 3 is 9. My second number, 6 on e to the 9, 6 on 2.7 to the power of 9. That bottom number is going to be huge. So because the denominator is huge, that means this number is going to be much smaller. So our absolute maximum is at x equals a third, y equals 2 on 3e. So that's just a note about if you wanted to estimate things, which can be quicker than pulling out a calculator. If you can look at that e to the power of 9 and go, actually, that's pretty huge, then that tells us that that y value at that third point is small, sorry. So we've got a step-by-step process for finding our absolute maximum and minimum, even if we can't sketch the graph. If we did want to sketch this function, it would look something like this. Where that's x equals a third. So that's roughly what our graph looks like, and it just trails off on the right. Okay, so we've got a step-by-step process for finding absolute extrema. We've got a couple of sort of application examples to finish up tomorrow, but they shouldn't take us too long. Okay. Thanks, guys, and I will see you back here again tomorrow. Hi, how's it going?
I'm all good, thank you. Yourself?
Yeah, pretty good.
Good, good. I have a question for you that perhaps I can test myself. So in these test inputs here, if you insert negative numbers, is that going to get you in trouble or confuse you?
So if you had negative numbers here,
Yeah.
so we'll just let Cam set up.